Hello everyone, welcome back to my channel. Today, we just noticed that DeepMind just released a new paper about how to train large language models to self-correct its outputs using reinforcement learning. And what's interesting about this technique is that so far it's the state of the art in self-correction, and it managed to achieve 16% and 9% of accuracy improvement in math and human eval benchmarks. So typically, what do we mean by self-correct? Well, in this case, it's about trying to evaluate on its own responses and see whether or not it itself has been hallucinating or not. If it does, it can then correct its own output afterwards, right? And it's something that you typically see in like the new open AI model called O1, right? Where they actually is like able to self-correct during its chain of thought reasoning steps. So we're gonna take a look into this paper, but I just want to let you all know that I just created a Patreon, and you guys can go check it out. Link is in the description below and in the comments. And and what this and what my Patreon allows you to do is that you are able to tell me what papers you want me to cover in the next few videos, and I will try to explain them to you guys in the videos, right? So links are in the description below. But for now, let's get right into the paper, shall we? So let's go through the abstract first. Okay. Self-correction is a highly desirable capability of LLMs, yet it has consistently found to be largely ineffective. It is always ineffective, especially if you're using one of those open source models that's like 7 to 8 billion parameters in my experience, right? Where it can't really like critique on its own output efficiently, even though if you like give it a lot of examples in order to start up its in context learning, but in that case it doesn't really work that well. So okay, so there are a few approaches for training self correction, and it typically uses multiple different models, or it relies on a more capable model. For example, if you are sorry, just a second, what the heck is happening? Oh, never mind, it's my neighbor. Anyway, yeah, okay, yeah. And the other approach is to like use a larger, more capable model like the 7 billion parameter models, and you try to use that to evaluate the outputs of the 8 billion parameter model. And there are other forms of approaches as well. Okay, but right in this paper, they mentioned that they developed a multi-turn online reinforcement learning approach called SCORE that significantly improves an LLM's self-correction ability using entirely self-generated data, right? But before that, we need to know what it means. What do they mean by online reinforcement learning? So okay, right. So online reinforcement learning kind of looks like this. You see, so when you're performing online reinforcement learning, what you're trying to do is that unlike offline reinforcement learning, where you have like a fixed batch of data set about the agent's action onto the environment and what's the reward, right? Instead, during online reinforcement learning, you don't have such data. Instead, you have to perform the learning, right, in real time. That's what they meant by online reinforcement learning, right? But there's also another part right here called multi-turn. Not so sure what that means, but pretty sure it's a common term. Let's look it up here. Okay, so what is a multi-turn? Okay, let's see. Right, and there's the tweet for the paper. Okay, right. So multi-turn is basically a multi-turn conversation in that way, and you're performing the online reinforcement learning for the multi-turn conversation style approach. Okay, that makes sense. All right. So, okay, and obviously the greatest part about this is is that it uses its own self-generated data, which is really cool. And this kind of reminds me of the star algorithm, where you bootstrap, where you collect some of the outputs, right? The outputs that's wrong, right? And then you try to ask the model to give the reasoning behind the supposedly true labels, right? And then you keep on doing this kind of loop of like improving its own reasoning capability, right? And this is somewhat similar to this approach, right? Because after all, both approach, this one and that one, it uses both self-generated data. But okay, yeah, so make sure to keep this in mind. Okay, but let's continue. Okay, to build score, we first show that variance of, so let's say variance of supervised fine-tuning SFT on offline model generated correction traces are insufficient. Okay, right. Okay. So, and to say that, okay, if you just like collect a batch, right, a fixed batch of data, right, and you perform SFT, it's not gonna be good enough, uh, as they say, right? So, okay, and in particular, they observe that training with SFT either suffers from, okay, let me use the red color here. Why SFT suffers from a distribution mismatch between the training data and the model's own responses, or implicitly prefers only a certain mode of correction behavior that's not effective at test time. So basically, with with, with this supervised fine tuning approach, it's kind of not working well for stuff that's like out of distribution in that sense, right? So it would be interesting to see why their approach can resolve these two major issues, right? So let's go on and read the next part here. Okay, SCORE addresses these challenges by training under its model's own distributed. Okay, so what I meant by here, okay, so they first train using the model's own distribution of self-generated correction traces, and then they use a regularization approach to drive the learning process such that it learns the self-correction strategy that works well during test time, right? As opposed to simply fitting a high reward responses for a given prompt. Okay, so there's two components here. One is to train using its own distribution of correction traces, and the other one is to use some kind of a regularization approach to make it learn a generalizable self-correction strategy, right? So, okay, Right. Let's see. Okay. This regularization runs a first phase of RL on a base model to generate a policy initialization that is less susceptible to collapse. Okay. Let's highlight that. Okay, that is less susceptible to collapse. And then using a reward bonus to amplify self-correction during training. Okay, right. So the first step. Okay, so the regular. Okay, right. So the regularization approach that they use, basically, okay, they first run RL, right? They train a base LLM model using RL to get some policy initialization that doesn't collapse. As most people might know, training a model using reinforcement learning is really difficult, right? Yeah, and it often leads to the parts of the training process where it just completely stops learning at all. Yeah, and this phenomenon is actually called uh, collapse, right? Okay, and the next part is that using a reward bonus to amplify self-correction during training. Okay, so there is a reward function, another reward term that specifically tells the neural network to perform more self-correction during training. Perhaps that's what it meant, but we shall see in the next few sections. Okay, so and then try it out on Gemini 1 Pro and 1.5 Flash models, and then found that oh yeah, it improves self correction by this amount of uh, percentage of accuracy, right? So okay, that's pretty interesting already, right? So let's see. Let's actually go to the. Let's see if there's a conclusion down here. Da, 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 da. There's a lot of diagrams. That's good. It helps with our understanding. Okay. Okay, that's the discussion. Okay, right, right. Okay, here. In this work, we investigated how to endow LLMs with a self-correction strategy that allows them to correct their own responses on fly at test time. Yeah, this is something like the O1 models been doing, right? Or maybe what we call it, the strawberry model. Yeah, 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 it's crazy to me that OpenAI is like keeping everything secret, but now Google is like publishing out papers that's kind of related to the O1 models at the same time. Yeah, I really do hope the research labs, I mean, the academia, should catch up on this approach so that we can get like an open source version of the O1 model. And I think there already is, right? Is it called Llama Berry? Uh, well, is it is it open source? No, 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 no. That's not the one. Yeah, yeah. The reason, yeah, it's called llama berry because like you. Okay. Do you know what? No, llama berry is not trained using reinforcement learning. Unfortunately, it is just a bunch of prompts in there. I think. Uh, yeah, it would be a shame if it's the case. Yeah, sorry if I'm going a bit sidetracked here, but I'm just curious if there's like any open source implementations. Yeah, those are just yeah. It's just like the reflection model. But yeah, it's just prompts. Yeah, just prompts. It doesn't say anything about uh self correction or reinforcement learning. Anyway, sorry about that. Okay. Specifically, we propose SCORE, a multi-turn online RL approach, so that they can correct their own mistakes, right, and demonstrate that it is the first method that can attain significant positive intrinsic self-correction performance. Okay. So they analyze the behavior of various fine-tuning baselines. Uh, Sorry, got to burp. And identify failure modes in which the model learns a non-correcting strategy, learning to make no edits. Okay, right. So there are a couple of fine tuning. Okay, so there are a couple of states of the model where it doesn't learn to self-correct itself. Okay, that's interesting. I mean, typically, reinforcement learning is kind of stochastic in the sense that you wouldn't really know what it's going to do, and it's most likely going to like cheat anyway. Uh, in the sense that it will find the simplest path to like get the most rewards, and that it doesn't really try to learn the behavior that you want it to learn. So yeah, RL is kind of tricky, right? It's not as straightforward as a supervised fine tuning in my experience. But anyway, yeah. Score is designed to elicit self-correcting strategy by using a two-stage structure and reward shaping, both which help to prevent the model from collapsing into not learning effective self-improvement behavior. Okay. Well, that's cool. All right, and then talk about some limitations of their work and some future work as well. Okay, and they say, oh, okay, this is interesting here. We did not train score for more than one round of iterative self-correction in this paper, which means that subsequent rounds of self-correction may not be as effective as the first one, which is something that we observe with the straw. Sorry, which is something that we observe with the star algorithm, where it kind of like increased a lot at the start, but it kind of like plateaus. Yeah, so there's definitely some diminishing return. So obviously, if you are interested in it, you could probably try to modify their architecture or algorithm such that it doesn't just plateau, but it can like do this exponential growth in some sense. Okay, so right, let's continue reading. Okay, which is already a common and effective practice to obtain self-correction behavior over more than two rounds with SFT. But in this case, they are not using SFT; they are using online RL. So yeah, try to do that, I guess. Okay. And then say, okay, the next part is unifying stages one and two of score is also something that you can look into, you all, yeah. Since that would alleviate the limitation of running multiple steps and help in designing a more robust method. So what this is basically saying, right? Okay, we haven't gone through what stage one and stage two are, but judging from this, right, if we can just like combine them together into a single stage, that would effectively make the entire approach more computationally efficient, right, and less expensive. But we shall go into that later. Okay, right. And let's talk about broader perspectives here. Okay, so okay, and this one is kind of interesting. So they say there's multiple implications of their work. Firstly, Learning meta strategies, okay, such as self-correction in this paper, might require going beyond the paradigm of SFT followed by single-turn RL. It demonstrates that multi-turn RL can provide one such approach, right? So the current method to create our conventional instruction fine-tune LLMs is to first pre-train it on a large corpus of data set, and then you perform supervised fine-tuning using instruction tuning data sets on the LLM. And after that, you have to perform some kind of a reinforcement learning from human feedback, right? But in this case, this paper tells us that maybe that's not enough, right? Maybe in order to make it learn this self-correcting behavior, we need a multi-turn RL approach in the pipeline as well, right? Okay, and second, the results also hint that perhaps using a more detailed or granular supervision when generating on policy rollouts in multi-turn RL may further improve the model's capabilities at implementing nuanced strategies. Okay, right. So even though score did not use dense, okay, so it doesn't use dense or fine-grained feedback. It is already able to improve the models. Okay, here's something that this reminds me of another paper. It's from OpenAI, right? Right? Kind of like okay, it's kind of like what they're trying to imply here, right? Is maybe we can combine some some concepts from a paper called Let's Verify Step by Step, and you can check it out for yourself. There's plenty of videos about that on YouTube, but it's basically this, right? Basically there is like two things that you have to keep in mind. One is that when you're trying to fine tune, or in this case RL, right? Okay, when you're trying to fine tune a large language model, right? You typically are only concerned about the outcome of the model inference, right? But but there's also another part that needs to be addressed, and that's the process, right? Uh, right. So in the paper, they have two different things. One is called the outcome reward model, and the other one is called process reward model, I believe, right? So the process reward model will check whether or not the the specific the specific text generation each step does it make any sense, right? So maybe this is something that that people can look into, right? Although they don't mention this connection directly, but I can predict that it would happen soon. So yeah, that's my interpretation of it. All right. Okay, dense or fine grained feedback, which is exactly why you need like a process reward model to do that, right? Yeah. So if you guys use this idea, please, please let me know. I would be happy to know if you guys use it. Anyway, okay. It was able to improve that. Okay. Utilization of the dense feedback is likely to complement our method well. Yeah, obviously, it has been proven. Um, Okay. Finally, the importance of our two-stage recipe based on careful initialization and reward shaping in obtaining positive self-correction, perhaps more generally, hints that some kind of regularization is needed to ensure that the LLMs can learn nuanced strategies that can achieve great generalization, right? Basically, it can handle things beyond the training set, obviously, right? Yeah, yeah. I mean, regularization in machine learning is pretty common. It's a pretty common approach to get high test accuracy. In this case, we see the same thing in these LLM papers. Okay, cool. So, right. That's a really good conclusion, I would say. There's quite a bit of results in here. So how about if we quickly skim through the introduction for now? Okay. LLMs are really good in reasoning and scientific domains and maths. Okay. Okay. An aspirational property of LLMs is to be able to implement algorithms, strategies that help LLMs to use computation and interaction to improve. Okay, to use computation and interaction to improve its response on test time. All right. Most LLMs do not implement algorithms reliably. For instance, consider a problem setting that requires models to detect and revise or self-correct their own responses to during test time, so as to be able to eventually arrive at the best possible answer. Okay, yeah, so self-correction isn't something that's easy to do, right, with the current LLMs. And to say that this is especially difficult when you don't have any kind of like external input, right? Mm. Also to refer to as intrinsic self-correction. Cool. Uh, okay, right. Okay, to make progress towards that, we study a special instance of training LLMs to fix their mistakes on the fly. This should be possible. Okay, I like this four words here. Um, on many queries where current LLMs fail, they still contain the underlying knowledge needed to arrive at the correct answer, but are unable to correctly elicit and draw inferences about their own knowledge when needed. Okay, I think this is a pretty big part right here. Is that the LLMs, they already know the correct solution, right? But the issue is that how do you get those correct solutions out? That's the challenge. So for instance, strong LLMs can complete a subpart of a mathematical proof when prompted with the remainder, but may not be able to do so from scratch. Okay. In a similar way, using their previous responses and should enable LLMs to improve their subsequent ones. Nevertheless, self-correction is quite difficult and it needs a lot of different approaches. So, okay, and the question is, how can we instill LLMs with self-correction abilities? And there's quite a few different approaches to do that, right? But not so reliable, I guess. Okay, so typically using prompt engineering, right? Basically just telling the LLM, oh yeah, okay, detect your own mistakes and fix them, right? But usually that doesn't really work that well. And another one is to just perform fine tuning on the models such that it is capable of self-correcting its own responses. Okay, right. And these methods often fail, right? it's pretty bad. So yeah, and they say, okay, the fine-tuning based approaches requires multiple models upon inference, right? So you need to have a separate verifier or refinement model, and you need an oracle supervision to guide the entire self-correction process, without which self-correction does not necessarily outperform independent uncorrelated attempts at the problem, which all in all means that it just doesn't work, which is kind of sad, right? So we develop an approach that is effective at self-correction without any of the above requirements like multiple different models and blah blah blah, right? Okay. Our approach self-correction, okay, right? Our score approach trains only a single model that can provide a response and a reasoning problem, right? And also correct errors despite not receiving any oracle feedback. More importantly, it teaches this ability entirely by training on self-generated data. Okay, right. That's interesting because if we want to further improve on this, right, then the process reward model needs to be the same model. The same model, right? Right. No separate different model. Wonder how they're going to do that in the future. Okay, so they started off by studying the failure modes of existing fine-tuning approaches, and they observed that running SFT on multi-turn self-correction traces coupled with rejection sampling. Okay, and I have an example here. Okay, a multi-turn variant of star algorithm often amplifies the model's bias to not make any error correction. Okay, right? A minimal edit strategy. Okay, a minimal edit strategy uh, appears to be optimal as it inhibits the model from sorry from learning to make correct responses worse in the second attempt, even though it does not instill self-correction abilities to the model. Okay. If the training set for SFT is altered to explicitly downweight certain correction traces that only make minor edits, then the resulting training is able to avoid collapse. Okay. Right. So what is stated here is that if I'm not mistaken, in okay, if you do not want the entire train to collapse, then you basically need to like make sure that all the correcting traces have the same importance weighting, such that it doesn't collapse. Okay, sure. However, it suffers from the curse of distributional shift, a correction strategy learned by training on off-policy data does not enable it to succeed at correcting its own mistakes, which basically means that yeah, during test time, the distribution uh, um, be, yeah, so the distribution during test time is not going to be the same as the distribution that you learn during your RL off policy training, right? So that's the problem with like this star approach here. So okay, so the method, right? Uh, okay, so their score approach tries to fix these issues, right? Right. Just by replacing this the supervised fine tuning method with a multi-turn RL approach. Okay, So in summary, it runs multi-turn RL on self-generated data in order to fix the distribution mismatch between training and test inference, right? So, okay, yeah. So to avoid failure mode of learning a minimal edit strategy, right? We train score in two stages. So, okay. Stage one, okay, so each stage tries to not let the model collapse on its own, right? So, okay, so here's the important part here. Okay, the first stage re replaces SFT. Okay, by training a model initialization that optimizes correction performance while constraining the first attempt to be close to the base model. So what this basically means is that yeah, so stage one is basically try to like, okay, do you have some parameters, right? Let's say theta, and you're trying to make it somewhat similar to the theta but RL. So the base weights and the RL weights are really close, right? Okay, so that's what they do there. And the second stage runs, okay, and this is where they get to run. Okay, second stage is when they get to run the multi-turn online RL to optimize a reward at both attempts while using a reward bonus term that encourages improving responses from the first attempt to the second. All right. So both the first stage, okay, so both initialization and reward bonus make sure that the model cannot simply learn to, okay, so it cannot to simply learn to produce the best first response. Hold on just a second here. Okay, no one's there. Good. Okay, and only minorly edit the instilling response, right? So basically, you want it to learn to correct really bad outputs, right? You don't just want it to like output the correct output. It makes no difference, right? It makes no difference compared to just simply training a LLM from scratch. It doesn't learn to self-correct at all. All right, so that's pretty understandable. All right. Our main contribution is score, okay, blah 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 blah, okay, and a claim that it's the first approach that gets positive intrinsic self correlate correction relative to their base Gemini models, right? So, and we shall see about that soon. But okay, so we're not gonna go through related work because like we already gone through a lot of stuff at the top, and it's mostly related work, honestly. Um, okay, all right. So here's where the difficult part comes in. So we have reached the methods. Okay, so there's preliminaries and problem setup, and then they talk about SFT, supervised fine-tuning, and why it's not enough for self-correction, right? And then after that, they talk about their analysis, setup, their methods, and how they construct the self-generated data set, right? Which is something we have to look into. And they also present some empirical findings. Okay, okay. And lastly, they talk about their approach, right? And they explain why it works. Okay. Okay. Okay, what should we do, guys? Okay. I tell you what we can do. Just give me a second. Hmm. Okay, what's the? Oh, yikes! 40 minutes already. Oh boy. Okay, how about this, right? We take a look at the figures first, right? Because this is another way. This is a very common approach to like read a really dense paper at the beginning is to just take a look at the figures because it can basically just like summarize the entire thing, right? So, okay, let's take a look at the first figure here. All right, on the left, okay, so their approach, okay, it gets score gets state-of-the-art self-correction performance on mathematics, and on the right, score inference time scaling, spending samples on sequential self-correction, okay, becomes more effective than only parallel direct samples. Okay, not so sure what they meant by parallel direct samples, right? But as we can see right here, okay, if you okay, why is it like this? Huh. Oh yeah, okay. Right. So their original approach. Okay, so here's how you look at it, right? So direct generation means the first attempt, right? So direct generation is when you just like, okay, do the model inferencing for the first time and you get the response, right? And you make a calculation, right? Then you get the results and then you compare it with the actual answer, right? In this case, right, it gets, okay, all right, just give me 1 second here. Okay, so they're using the same model here, but from what I'm seeing here, okay, the test accuracy is different. And this one is much higher for some reason. Huh. Why is that the case though? Shouldn't it be the same? I mean, you are using the same model after all. But but anyway, I think we can look into that later. But I think the most important thing right here is to look at the gap, right? So if you take a look at the blue column right here, that's basically the accuracy that you get after you put in that self-correction mechanism into the model, right? So as you can see, if you just simply prompt the LLM to make some self-correction, it just falls flat completely, right? No positive improvements whatsoever. But now let's move on to star, right? For the star algorithm, it increases slightly, right? As for supervised fine tuning, it increases close to 2%, whereas for score, it increases by 4.4%, which is the highest accuracy improvement in this case. Um, let's see. Yeah. So right here on the right hand side, they have a graph that shows us number of samples versus self consistency at the number of samples. Okay, so apparently using self correct is higher than parallel samples. Not so sure what that means. I mean, it's directly referring to section 6.2. Okay. Why do you have to put this figure at the top? It's confusing. Uh, yeah, you should probably put it at like page 8 or something. Not at like page 2. It's ridiculous. Um, or maybe I'm just dumb, you know. Okay. Let's look at the second figure here. Okay, figure 2, an example trace and the problem setting of self-correction. Okay, right. This is where the fun part begins here. Okay, so this is their algorithm in action here. Okay, so you state the problem. Okay, so the maths problem here. Okay, and this is okay. So the first turn, right? The LLM gets the answer wrong. It's incorrect, right? I'm not gonna check that, but I would assume it's incorrect because they say so. And then and then it generates, and the same model itself, it generates a self-correction instruction. Uh, okay, right. And it says, oh yeah, there might be an error because I myself don't understand the question. I need to correct myself and rewrite the solution. Okay, so it's kind of whispering to itself right now. And all of a sudden, it got the correct answer. Okay, so look. In this fashion right here, it seems like there. Okay, what should I say here? It's kind of not like strawberry in a sense, right? Because if you ever go on Reddit or some places, they do like show some behind the scenes of like, oh yeah, the chain of thought reasoning, and then how it can like, aha, I made a mistake, and then yep, I correct the mistake in some way, right? So in that sense, it is more interpretable to us, right? Because it is directly written down. All the reasoning steps are out there, right? But in this case, it's just like so opaque, right? Right. It doesn't say much. It just says, "Yep, you don't understand it." Well, it is what it is, right? But what I try to say is that the self-correction approach is kind of like a black box, right? Something which we don't really understand, right? Because it doesn't really show up here, right? So anyway, okay, let's move on to the right hand side of the figure. We have standard training. Okay, which is basically just your ordinary supervised fine tuning, where you give the LLM your prompt and you generate some kind of response and you compute the loss function using the response and you train the foundation model using stochastic gradient descent. Okay, so, and here's their approach: training using score. So, okay, so, yeah. And now let's say, okay, score trains the LM to not just produce the best possible, not just the best possible response, but it aims to train the best final response the best final response in the final attempt. In the second turn, extra input in the form of an instruction, asking the model to correct itself or model generated may be provided. Okay, so we start off with prompt input into the LLM, and it creates its first answer. right? And then, okay, so far it is identical, right? If we cut this part of it is identical to the supervised fine-tuning approach. But here's what they do afterwards is that they feed in the input, right? There's input tokens right here, and they also have some kind of like external input P, right? And then it asks it to generate a second response. And here's the trick that they do, right? So they ask it, okay, I'm just going to evaluate your second response, right, using the loss function, and that's it. Okay, it looks so simple. Man, why didn't I come up with this approach? Oh man, yeah. I mean, you could theoretically like stack it up, much like an a RNN, a recurrent neural network in the sense, right? But instead of feeding it to the to the same place, you're like feeding it to a single model, right? It's yeah, yeah. Anyway, it's kind of like an RNN in this case, which is pretty cool. Okay. Right. Let's take a look at table one here. Okay, table one, self-correction performance after training on a star dataset and SFT dataset. For both approaches, we find that the gap between second attempt and first attempt to be overly negative or small. In that case, it doesn't work, right? It just doesn't work. Yeah. In addition, both approaches oh my god, detriments the correct response to be incorrect. That- Yeah, I see this plenty of times, man. It's like, oh my god, yeah, there's like my LLM is able to like, okay, it generates something that's like 99% correct, but after self correction, it is like unusable. It's like just 40% correct, which is abysmal, right? Okay, so yeah, I feel like you guys should already know that by now. Yeah, so it's pretty horrible. Okay. Right. In addition, okay, right, reflected in the high C to I. Okay, what is C and what's I? Uh, okay. High C to I, high C to I. That's bad. Okay, so the higher this is, the worse it is. So this is a bad one, and this is a good one. Hmm. Okay. I see it now. Yeah, that's pretty bad. Um, yeah, I mean that's improved a bit, but this one's way worse. Right? Yeah. So let's see right here. Yeah, yeah. So okay. Let me see you just a second. Okay, right. So C stands for correct, and I stands for incorrect. God damn it. Okay, right. So, okay. Okay, right. This is pretty bad. Yeah, it just sucks, right? It just sucks all the way through. Oh man. Okay. Anyway, I think that's that. Next, self-correction performance after training on D plus star and D plus SFT. Okay. Uh, Performance improves for star, indicating that a higher coverage dataset helps improve performance. Okay. I assume that sorry, it's not star, it's plus, right? I assume the plus sign just means that it's a larger coverage data set, right? So, okay, but not for SFT, where training on traces on both responses are correct, forces the model to simply not make any changes, no matter how correct or incorrect that is. Yeah, it's pretty bad. Yeah. Um, sorry, just had another word. Yeah, I mean, yeah, a word just sucks, right? This is just yeah. So these two tables right here just shows how the previous approaches just suck monkey balls. Okay. Anyway, right. Right. Let's see. Figure tree. Okay. Figure tree right here. Okay. Oh yeah, but before that, we should probably take a look into what an edit distance is for those who do not know. So an edit distance is, okay, according to Wikipedia, it's a way to define the distance between two strings, right? So if you guys know, there's a way to like compare how different two sentences are, right? And usually you by using neural networks, right? Especially with like the BERT encoder models, right? You can then generate the embeddings of the sentences, and then you can like measure either their cosine similarity or their Euclidean distances, and so on, right? But this right here, the edit distance is a more primitive approach where it's just counting the number of operations that's required to transform one sentence into the other, right? And that's the basic explanation. So, so we take a look at it right here. Okay, let's see. Are there any like good examples here? Okay, right. So it's something like this, right? And then you add up these highlighted traces here of this matrix, and I think that's the edit distance, I believe. I could be wrong. Okay, right. Edit distance between. Okay, so the difference between the first attempt and the second attempt responses obtained from fine-tuned models, our approach and the base model, right? Observe that while training on a self-generated error correction traces inherits a bimodal distribution of edits as the base model. SFT tends to be quite conservative. Okay, this right here, this is a very juicy info right here, right? So it says that, okay, if you train it on its own self-generated error, just like how Score their approach did, you usually will have a bimodal distribution, right? But for SFT, I guess that's not the case, right? So let's take a look here. Where's SFT? Okay, right. Here's what they meant, right? So if you take a look at the base model, right? It's kind of like this. And then as for the self-generated data approach, it's a bimodal distribution, right? But take a look at SFT. It's a unimodal distribution. Wait. Oh, wait. Just give me a second here. Wait, how about the score then? Score kind of looks like a unimodal distribution as well. What the heck? Okay. Observe that while training on self-generated error create inherits by all the okay. Maybe I'm missing something here. Bimodal distribution. Let's have a look at that. I'm yeah, I know what a bimodal distribution is. Okay, then why is it like a unimodal distribution? Why? Why is it like a unimodal distribution? Huh, why? Um, okay. Let's wait. Okay, these are the histograms of edit distance ratios on the math dataset. Okay, right. Right. Wait a minute. Okay, so right here, part B, start edit distance ratios. Okay, so basically you're just saying like, oh yeah, our distribution on the training part and the eval part are pretty much like identical, right? But as for pair SFT, it's okay. All right. This kind of looks like a Gaussian, while this one kind of looks like something else entirely, but they don't really explain more, right? In that case, I would even say, oh yeah, score is like training on its own self-generated error correction traces, right? So, but you say that it looks something like that, but that's not the case. It kind of looks like a single distribution. I don't understand that part. They probably explain it in the text, but I tell you what, let's keep on looking at the figures for now. Figure 4, tracking self-correction performance on different sets of first attempt responses. Fixed validation. First responses distributed identically. Okay, fixed validation. Okay, so there's fixed validation, self-generated. Okay, first response is distributed identically to the training set, and B, self-generated. First response is generated by the learner itself. Okay, what is this trying to do exactly here? Tracking self-correction performance on different sets of first attempt response. Okay, I get it now. Guys. Okay, right. So the fixed validation part, okay, it could be referring to, okay, we put in the correct, I, I mean, oh, yucks. Okay. We put in the correct response for the first, as the first response. Okay. As the first response, and see how the LM makes the second one. Okay, or something like that. Not too sure. All right, and self, because like it's saying, oh yeah, self-generated is when the first response is generated by the LM itself. Okay, let's continue reading though. Observe that over the course of training, while accuracy of correcting a fixed validation set of responses largely stays constant, slightly improves. The accuracy on training data improves substantially. Okay, well, no, no poop, right? I mean, it's obvious though. Basically, it's not generalizing that well. It's just fitting to the training set actually. Note the different axes for the training set accuracy on the right. The model's correction abilities, its own first attempt response degrades. So, this one right here, that's important. The model's correction abilities, its own first attempt response, right, degrades substantially. This tells us that that training on a fixed offline dataset may not be effective at inducing self-correction abilities due to distribution shift, right? As you can already see, even for the validation set, right, it doesn't improve that much to begin with. So let's move this text here. I just want to look at the figures myself. Okay. Okay, this is the incorrect to correct, right? And that's response one and response two, right? As you can see, right, just by using SFT, right, the validation accuracy kind of drops at first and then it just climbs back up a bit, but it's not doing much. Whereas for, wait a minute, wait. Yeah, uh, yeah, I could be misunderstanding here, but okay, so basically training accuracy increases as well as for like right. So as for the okay, right. Self-generated validation decreases while for the fixed one it increased a bit. Right. All right. So that's that. Let's take a look at here what they have to say more. Takeaways. Okay, so some ideas, right? Wait. Okay. All right. So they show two distinct sources of failures of supervised fine tuning, and here's what they claim so far. The star algorithm only adheres to one mode of correction behavior that make minor changes, and training using pair supervised fine-tuning on data with wider coverage results in worse self-correction abilities due to distribution shift, right? So obviously we need an approach that can directly train on self-generated traces, and then it should prevent the model from making like small changes because that's not efficient. That's not great. Okay, and all this work, right? Just to say how their competitors are pretty bad. Okay, broader implication. It also suggests that offline SFT is really bad, really bad. Okay, and now we have come to the meat of the paper, their new approach score. So okay, what do they have to say in this part right here? So they have so they talk about stage one trying to get the model to not collapse, and stage two of RL training. Okay, they talk about some reward shaping. okay, and some hyper parameters. Okay, right. Okay, let's quickly go through this. It's not that long. Okay. Oh dear. Okay, so to create that, their approach. Okay, let's see. Let's see right here. Okay, there's a lot of text here, but I think we should look at the figures first again. Okay, okay. Figure 5a, evolution of training reward with more training, with more epochs, you mean, right? Okay, when training with naive multi-turn RL, the responses are become tightly coupled together, leading to poor convergence for longer iterations. Okay, stage one in score is designed to fix this problem to increase exploration and better final performance. Okay, but we shall see it ourselves right here. So let's see. Okay, so this is turn two, turn one, turn two, turn one. Got it. And okay, okay. You see it here, folks. You see it here. Their approach is much higher. Look at that. So this is like around 69, 69%, and this right here is like yeah. So yeah. So because this is a multi-turn thing, that's why there's two lines, and the other one is 64% maybe. Yeah, yeah. So it's much higher than their baseline. That's cool. Okay. Frequency. Okay, next figure right here, figure 5b. Frequency in which the learner proposes a different answer in the second turn. Wait, just give me a second. Hmm, hmm. Okay, let's go. Frequency in which the learner proposes a different answer in the second term. Okay, this is very interesting. So, so proposes a different answer, right? Okay, so and say without without explicitly modifying the initialization of the policy in their approach, right? They show that the policy quickly learns, okay, it quickly collapse. In this case, it's collapsing into a state in the state space where it doesn't make any changes to its answer, right? And that's pretty bad. And this and the symptom is that you can see a decrease in the number of prompts for which the second attempt produces a different answer. So as you can see right here, so okay, there's a plane. Anyway, yeah, as you can see, there's a major drop, right? As soon as you don't use their policy initialization, is that as you continue training throughout the process, right? The the answers that you're getting, right? is about to become similar and similar and similar over time, and to the point that it might even reach to 0%, right? Whereas for this one, right, it's it's still dropping, right? I mean, I guess it's still dropping to some extent, but it would be interesting to like pull this axis all over to the right and then see whether or not it can even like converge to like zero at all, right? Or maybe there is some theoretical limit to how similar the answers can be, right? So that's another different thing that they can try in the future. Um, okay, here, figure 6, an overview of their approach. Okay, so their approach is like this. Score trains a model in two stages, stage 1 and stage 2. Okay, so stage 1, train and initialization for self-correction. Okay, so basically, constraint to base model. Okay, so first attempt, yeah, which is basically the same thing that we talked about at the above, right? And then, okay, and then maximizing reward somehow. And then, okay, stage 2, run multi-turn RL with reward shaping. And the task is to maximize shape reward, and the first attempt is focusing on maximizing its own reward. Okay, and let's see right here. Okay, stage 1, instead of okay, stage 1, train a good initialization that can produce high reward responses in the second attempt while mimicking the base model's initial response at the first attempt. All right. Stage 2, jointly optimizing both attempts, where the latter uses a shape reward to incentivize discovery of the self-correction strategy instead of the simple strategy of producing the best first response followed by minor edits in the second attempt. So we shall take a look at the reward shaping because that's the key method. All right. So, but before that, let's take a look at the result here. So obviously, right, obviously they are not going to just publish a paper with bad results. And this is what they got here. So, okay, so the ability for their method to mess up the entire thing is just 1.4%, right? Whereas self-correction is 5.8%, right? And 4.4% accuracy of improvement, as you can see right here. At the first response, it gets 60%, which is pretty good compared to the other approaches. But as soon as you get to that self-correcting phase right there, it gets up to 64%. Yeah, overall it's really good results. But yeah, so let's see. All right, so it doesn't get the first one correct, and then all of a sudden to apply its self-correcting mechanism, it gets up to 64.6%. All right, so this one is low. That's good. This one is pretty high for human eval. Impressive. Score. Okay, right. And here comes their ablation right here. So okay, a score. Okay, so this is their complete approach. All right. Honestly though, we should only care about this and this. This one is not so important, right? Because we only care about how it can improve from T1 and to T2, that right? In fact, I would say it would be more impressive, right, if the T1 is like really bad, right? But but your T2 is superb, right? So so in this case, what you really want, right, is a T1 to like drop in accuracy, but you want T2 to be like really high in accuracy, right? Okay, and obviously if you remove any components, right, you typically get a reduction of accuracy improvement, and that makes sense, right? So let's see. Huh. Stop. Okay, let's see. Okay, so that's that. Hey, finally. Okay, let's go through the equations. I'm really curious about it right now because it feels like something we can probably use. Um, so it's gonna be pretty hard, especially if there's no like open source code on GitHub. I don't think so. Um, but with the equations, that's all it matters, baby. Okay, stage one. This is the equation. Maximize the expectation from some kind of like distribution, blah blah. Maximize the reward hat. There's some hyper parameter and some k KL penalty. Okay, and here's where to say, right? Okay, a strict KL penalty only on the first attempts to avoid shift of the first third responses. Okay, note that we still utilize the default KL penalty, KL divergence penalty. Okay, right. Uh-huh. Let's see here. Okay. I see it now, guys. I see it now. So, okay, it's pretty simple. So if you take a look at here, right, the reason why they even call it like, oh yeah, constrained to the base model. Okay, that's because, right, when you apply gradient descent, even on this part, right, the fact that the gradient can flow to the first attempt response means that it is also, the model is also able to make the first attempt much more accurate one, right? Right? So in that way, right? Yeah, if you let the gradient flow and make changes to the first attempt, it basically just like, oh yeah, you can make the best first attempt, and for the second attempt, you can just make minor corrections, and that's not exactly what you want, right? So this is what they meant by constrain the first attempt to the original model response, right? You do not want the first attempt to change in any way or form. I understand it now, guys. I understand it now. Okay, cool. Right, and I hope you guys get it as well. I'm pretty sure I'm right in this case. Right, okay. Stage two. Okay, multi-turn RL with reward shaping. All right, so let's see. Okay, scored trains responses at both attempts to optimize the reward. Of course, we want, okay, right. We want to make sure not to degrade the first responses in the process. Okay, so they try to maximize the expectation of the reward minus, yep, so the regularization is right here. Let me, let me try to read this. Ah, yes, yes, okay. As you already know, right? Okay, there's like two attempts, right? Two different responses. The first one and the second one, right? So it's described in the sum term right here, where you have the summation, right, of this, right, such that you have I equals to 1. When I equals to 1, it's applying the regularization, right, for the first response, and I equals to 2 means that it is also applying the regularization to the second response as well. So it's pretty much quite similar to this in that sense, right? So you sum them all up together and you try to uh, perform gradient descent with that. So okay, and right here, reward shaping to incentivize self-correction. It is unclear if running RL for optimizing this equation prefers a strategy, right, that that promotes self-correction. Yeah, it's no, we are not quite sure about that, right? Let's say so to fix that, right? Because like both approaches seems to be equally good, right? So they want to bias the learning problem by placing more emphasis on to traces that flip correctness from the first attempt to the second attempt. Okay, right. So basically, they want the first attempt to be wrong and then have the second attempt to be correct. Yeah, is it this one? I wonder. Something like that. I forgot. Yeah, I to C, right? I think so. Okay. Okay. Concretely, given a two-turn on policy rollout, this, and this, where X to blah blah blah. Okay, right. We propose to modify the reward used for trading in equation 4 at the second attempt with an additional bonus term called B hat something. Okay, what does B hat do right here? Ah, okay. So B hat is essentially the reward of getting the second response correct minus the reward of getting the first response correct, right? Okay. And alpha is a hyperparameter, a multiplier, a real number that's significantly greater than 1. Okay. Let me guess. You increase the significance of the y2 reward and you try to degrade the significance of the y1 reward. Okay, makes sense, makes sense. Okay, adding this bonus to the second attempt only emphasizes and places heavy negative penalties of transitions that change the correct response to incorrect in the second attempt. In contrast, transitions that do not flip correctness are likely to collapse of not making any meaningful edits. Thus, the addition of this bonus should regularize the training process from collapsing on to the direct solution, right? But it doesn't have the self-correction behavior on the examples. Okay, this is pretty cool. This is pretty cool, and it's very simple. It's so simple. Oh dear. Okay. Yeah, that's not really that important unless you want to implement it directly, right? Yeah. Okay. Cool. 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 Yeah. All right. Yeah. I guess that's it for this paper then. Yeah. Yeah. So what have we learned so far? this paper is essentially teaching us like a really simple trick, right? It's all about tricks these days, right? And I forget about scaling. Scaling is only going to like get you so far, but these tricks are pretty ingenious in my mind. I have to admit that a few months ago, I've been thinking about something like this too, but yeah, but it seems to be missing some parts that would make it work, and I guess it has been solved in this case right here. Damn it. But yeah. Anyway, I hope you like this paper, and yeah, and do make sure to check out my Patreon if you want to. Yeah, yeah, and make sure to become a member if you'd like to. Yeah, so yeah, if you want to be a member, you can get the annotated papers that I make for each video, and you also can get to like decide on what paper or topics that you would like me to cover next. And obviously, I will put up uh, your names onto my videos as well as a way to thank all of you for supporting my channel, right? So yeah, have a great day, guys, and I will see you guys in the next video. Bye bye. Okay, let me just close this. See ya.